Well, good morning. I didn't realize that we were 3 minutes late getting started. It's 11:33 on Thursday, the 14th of February, Valentine's Day, and everybody must be visiting their sweetie because nobody's in class right now. So hopefully someone will be showing up soon. But we'll go from the current slide here, and when someone comes in, then I'll mess with the announcements. But for right now, we'll just leave it like this. And unfortunately, the day's really overcast, so I'm going to have to turn on the light on this side to read the book well. Okay. So, last time we had just started talking about multiplying two matrices and had given all the theory and the background for it, and had actually done a couple of real simple ones. Now in example 5, we do some that are a little more involved maybe than the others. So here, example, this is on page 44. We're in chapter 2, which is matrices, 2.1 operations of matrices, and this is multiplication of two matrices. Here's example 5a, starts with these two matrices. Let me get my pen set up. Okay. First of these is, and I usually read across, you can read down if you want to, 1, 0, 3, 2, negative 1, negative 2. That's the first matrix. The second matrix is negative 2, 4, 2, 1, 0, 0, and negative 1, 1, negative 1. Okay, and they have them set up as if they're going to multiply. Well, first, let's check and see if you can multiply. First, what's the size of the first one? 2 rows, 3 columns, that's a 2 by 3. The second one's 3 rows, 3 columns, that's a 3 by 3. Can you multiply? Yes, you can, because the two middle numbers are the same. So sort of toss them out, and the product matrix will be a 2 by 3. Okay, so set it up to do a 2 by 3. That's 2 rows, 3 columns. Okay, now you don't have to do it this way. I found this is the most, in the Navy we used to say you have to make everything sailor proof. I'll try to make this student proof, that not even a student can screw it up. So, but maybe you can, I don't know. But this is how I usually do it, just because this sets it up. Now, you pick a value here. It doesn't matter which one you start with. I always start with upper left and go across. I'm sort of anal retentive that way. You can do any one of them, but pick one, and then you say, what row, what column? Well, that's the first row, first column. So you take the first row of the first matrix, first column of the second matrix, and multiply and add as you go. That's a minus 1, 0, minus 3, I'm sorry, minus 2, 0, minus 3, that would be a minus 5. Next entry here is a 1, 2, first row, second column. So first row of the first, second column of the second, that would be a 4, 0, 3, that would be 7. Okay? Then you do, next entry is the 1, 3 entry, that's first row of the first one, third column of the second one. That'd be a 2, 0, minus 3. That would be a minus 1. Okay? Then you go to the 2, 1 entry. That's the second row, first column. So you do second row, the first matrix, first column, second matrix. Minus 4, minus 1. That'd be minus 5. Plus 2 would be a minus 3. Okay? Then the 2 entry would be second row, second column. That would be 8, 0, minus 2, that would be 6. And then the 2, 3 entry, second row, third column, do those and you get 4, 0, minus 2, so that would be a 2. All right, I did them fast. I hope I did them right. Let's see what they got. Minus 5, 7, minus 1, negative 3. Whoa, I did mess one up. That last one, 2, yeah, that's 4, 0, minus 2 times minus 1 is plus 2, so 4 and 2 is 6. Okay, sorry, I said I was going too fast, and I was. Okay, 6. Okay. Yep, got it. That's how you do, except don't make mistakes. Okay. Let's go to the B one. Since I'm not sure I have enough room here, let's go to a clean slide and let's do B. B is even smaller, and I think you'll find pretty interesting. 3, 4, negative 2, 5, multiplied by as 1, 0, 0, 1. All right. Now, first, can you even do it? Let's see. This is a 2 by 2, multiplied by 2 by 2. And sure enough, the interiors are both 2, so throw those away. Your resulting matrix, your product matrix, whatever I'm doing there, I'm not sure. The resultant matrix will be the outside here, a 2 by 2. Okay? So you'll have 2 rows, 2 columns. Okay? For the 1, 1 position here, you do first row of the first one, first column of the second. 3 plus 0 is 3. The 1, 2 entry here, first row, second column, 0 plus 4 is 4. And the 2, 1 entry, second row, first column, negative 2, 0, be negative 2. And in the 2, 2 position here, that would be second row, second column, 0, 5. All right, sure enough, it does seem to work. Look at that, though. It's the same as our first matrix on the left. Okay? Well, what does that mean? That means that this thing we multiplied it by, which looked pretty unusual, didn't it? 1, 0, 0, 1. It only had 1s and 0s in it, and 1s were on the diagonal, 0s everywhere else. We have a name for that. Now let's think back to math for a moment here. If you had 17 and multiplied it by 1, you get 17. You get A, you multiply it by 1, you get A. You get negative 4 million, multiply it by 1, you get negative 4 million. Multiplying by 1 produces the same thing you just had, right? We call 1 the multiplicative identity element for, in the real number system. Well, we just multiplied a 2 by 2 matrix by 2 by 2, and this one is called the identity matrix. And what is the identity matrix? It's 1s on the main diagonal, 0s everywhere else. Okay? It's basically what you do when you did Gauss-Jordan reduction. If you had a square matrix you're doing to and wound up with a leading 1 in every row, then you wound up with an identity matrix. Gauss-Jordan, remember, you eliminated you kept 1s in all the diagonal elements and 0s above and below every one of the 1s. So sure enough, that is what we call an identity matrix, because any matrix that you can multiply by that and do, you get the same matrix. Okay? So that could have been a 3 by 2 by a 2 by 2. It could have been a 17 by 2 by 2 by 2. It could have been a 1 by 2 by that 2 by 2, and you're going to get the same matrix at the end. Okay? Identically the same. All right, let's go to C. All right, let's see if we can do C on this page. C happens to be 1, 2, 1, 1 times negative 1, 2, 1, negative 1. Okay. Well, sure enough, this is a 2 by 2. Multiply by 2 by 2. Wipe out the middle 2's. They're the same. And you're left with a 2 by 2. So we're going to have a 2 by 2 here. 1, 2, 1, 2. Okay? That first entry is in the 1, 1 position. So you do first row by first column. That would be a minus 1 plus 2 would be 1. Then the next entry is a 1, 2 position. First row, second column. That'd be 2 minus 2 is 0. The next position there is the 2, 1 position. So the second row by first column, you get a 0 plus 0. -1 plus 1 is 0. And then the last entry is a 2, 2 positions. The second row by second column would be 2 minus 1 is 1. Whoa, we just got wound up with an identity matrix. Okay? Now, later we will know what to call that second matrix here, or the first matrix. Okay? Right now we don't. Okay? If I'll remind you of this in multiplying numbers together, let's say you had a 7, and you want to multiply it by some number, and you want to get the multiplicative identity element of 1, what would you have to multiply it by? Well, 1 over 7. 7 times 1 over 7 gives 1. Okay? 7 times 1/7 is 1. -3 times -1/3 gives you 1. -4 would require you to have a -1/4 to give you 1. Okay? 7/3 would require you to multiply it by 3/7, the reciprocal. Okay? It's also called the multiplicative inverse element. Well, we don't have really multiplicative inverses in matrices. We just call this the inverse matrix. Okay? Anytime you have a matrix that relates to some other matrix, and by the way, let me think and make sure before I say this, I think for this to work, they have to be the same. Yeah, they've got to be the same size. Okay. Some things in matrix multiplication they don't have to be, but this one they do. And when you multiply two matrices together and get the identity matrix as the product, then those two matrices are identical in the product of each other. I'm sorry. Right after my last class was over, I sat in here and cleaned up a few things on the thing, shut down that stuff. And starting to walk out and just went into a sneezing fit. And the bizarre thing is, yesterday morning, after my first class, this was my second class today, but after my first class, because I don't have a 8 o'clock or 8:30 class on Monday and Wednesday. I just have a 10 o'clock class. And when I was back in the office, maybe a little bit later in the morning than it was this time, but before my second class started, I had just the worst sneezing fit. And for the rest of the day, my head was clogged up. Well, it just seems to have happened again. Like I said, I was walking out of the room and just got to sneezing, and now I've got so much drainage that I can hardly clear my head. So sorry about the interruption here. But those two matrices, later we'll identify those as inverse functions of each other. Okay? Just like 1/7 is the multiplicative inverse of 7. 2/3 is the multiplicative inverse of 3/2. Okay? They multiply to be the identity element, which for numbers is 1, for matrices are the identity matrix. One of the identity matrices. Okay, let's go to the D one here. Sorry, my throat is just, my voice is just leaving me. All right, so here is the D. We start with a row matrix, which is also called a row vector. 1, -1, -2, -3. Can't talk. Multiply that by a column matrix, or a column vector, 2, -1, 1. Now, can you do that? Well, this is what? A 1 by 3. 1 row, 3 columns. This happens to be a 3 row by 1 column. And sure enough, the 3's are the same, wipe them out, And what you'll get here is a 1 by 1, which is just a single entry. So since its address is 1, 1, you do the first row of the first matrix, which is the only row, by the first column of the second matrix, which is the only column, multiply and add. You get 2 minus 2 is 0. Whoops. 2 plus 2 is 4. I keep messing that up today. Minus 3 is 1. Now, this is sort of a little bizarre here. That happens to be the identity matrix for the 1 by 1. So I guess you could say these two are inverse matrices of each other, but we don't, okay? And the reason is, to be an inverse matrix, they have to be the same size, and they have to be square. So these two don't qualify. They're not the same size, and they're not square, okay? So we'll leave that off this situation. That's not an identity. That's not a inverse matrix because they're not the same size. All right, so let's do E. It's sort of reverse of that. In fact, it's exactly the reverse of that. 2 minus 1, 1, multiplied by 1, negative 2, negative 3. Okay? Can you multiply those two? Well, this is a 3 by 1, 3 rows, 1 column, and this happens to be 1 row by 3 columns. And sure enough, the common interior values are 1, so throw those out. Your answer is going to be a 3 by 3 matrix. 1, 2, 3, 1, 2, 3, 1, 2, 3, because what's left here is 3 by 3. Sorry, I got to pause for a minute. Another issue I had today, I had several students in my previous class stop and ask some questions and do various things, so I was really late getting out of here. And so when I got down to my office, usually between these two classes, I try to eat a granola bar or something because I get so hungry this late in the morning because I eat pretty early in the morning to get into work on time. And I didn't get to do that today. When I got down to my office, I only had 3 minutes left. I didn't have time to eat a granola bar. So I'm up here now. My stomach is growling so loud, I'm surprised you can't hear it from where you're sitting, but I don't think you can. All right, so here we have the answer's got to be a 3 by 3 matrix. Well, this first is a 1, 1. So you take the first row of this, which is just the number 2, by the first column of this, which is just the number 1. 2 times 1 is 2. Do the same thing for the 1, 2 position. First row here, second column, that's a minus 4. Then the first row here, third column, minus 6. The second row, first column, negative 1. Second row, second column, 2. And second row, third column, 3. Okay? The next entry is the 3, 1 entry. So third row here, first column there, 1. 1 times negative 2 is negative 2. And 1 times negative 3 is negative 3. Okay. So here you have, and this is definitely not an identity matrix, nowhere close, okay? Not anything like except it's square, but that's all. So if these had been inverse matrices of each other, then they would have been commutative, and these are not. So that's the other reason you know these are not inverse matrices, just because the first one did yield, by happenstance, an identity matrix. So they're not inverses of each other. So that, I think, was example 5E. So, sorry. Let's get back to systems of linear equations. Okay? Remember, this is a 3 by 3 system. A11X1 plus A12X2 plus A13X3 is equal to B1. A21X2. Oh, my stomach hurts. No, that's X1. I knew something looks fishy there. A21X1 plus A22X2 plus A23X3 is equal to B2. And A31X1 plus A32, sorry, I had to stop and get my breath, X2 plus A33 X of 3 is equal to B2. All right. I am so sorry. I may need to go down to the bathroom and just clear my head because it's getting hard to breathe. I think I'll do that. So I'm going to pause this for just a minute, and I'll be right back. I'll try to get here as soon as I can. Yesterday, I didn't have an 8 o'clock class, so I worked in the office. And then at 10 o'clock, I did my Cal 1, okay? And then I was in the office for a little while at lunch, and right before I was going to start my Cal 3 class, I just had a sneezing fit. I mean, I'd been fine all morning. And then when I went to teach the Cal 3 class, I was just like this, and then drainage, and it was just awful.
I usually, when I get drainage like that drainage.
Yeah. Well, today I had 8:30 class and a 10 o'clock class, and after the 10 o'clock class, I had students asking questions afterwards, and I was finished up, loading and stuff like this, and then went down to swap out books, because from my calculus to linear algebra, and lo and behold, just started sneezing like crazy again. I'd been clear all morning, everything fine, and then went down, swapped out, came up, and the more I talked to it, and then too, I was so hungry. So I went by the office and got a swig of soda, which isn't going to satisfy me very much, but it at least gave me something, a little bit of sugar or something to boost. Yeah. So, where we left off before, I had done example 5, had 5 parts to it, so that's all. You can listen to that. I just set up the top of the next page, page 45, systems of linear equations. We've done this before, but now we're going to do slightly different with it, okay? Here is your typical setup for a 3x3. Your coefficients have double subscripts. The first subscript is a row, second subscript is a column, okay? And your variables are x1, x2, x3. You could do x, y, z, it doesn't matter. Your constants at the end are b1, b2, and b3. Just to say the constant for the first row, constant for the second row, constant for the third row, okay? Now, what we're going to do differently this time is not just go to write a matrix and then do row reduction, Gauss or Gauss-Jordan elimination. We're going to note that you can write this as a matrix A, you know the elements of that, times a vector B, X, which I can't write bold, so I'm going to do this, also is a column matrix, is equal to another column vector or matrix B, okay, where your A is, the matrix A is just as before, A11, A12, A13, the coefficient matrix, A21, A22, A23, and A31, A32, and that's a pretty ugly A, it's even worse, 3, 3, okay? And then your x column vector is going to be x1, x2, x3. Now, why do I make it a column vector and not a row vector?
Because it's only a single. You want.
What size is this?
It's a
3 by 3. And if I'm going to multiply, this has to be a
Right, that's his.
3 by 1.
Right.
You can't do a 1 by 3 because the middle numbers aren't equal. So
Right.
that has to be a column vector. And then what would the result be? Why couldn't that be a row vector? B1, B2, B3. Well, because this is a 3 by 1. No, a 3 by 3. This is a 3 by 1. Wipe out those. This has to be a 3 by 1 as well. So yeah, the nature of matrix multiplication dictates that those be column vectors. No choice. And I forgot to mark you here when you came in. So let me mark you at the same time I'll mark Daniel. Daniel, you've been marked. Okay. All right. All right. Now, we're on the top of page 45 in section 2.1. We just defined this way of expressing a system of equations. Different from what we've done before. What we've done before is not even mess with the variables at all and just done an augmented matrix with the coefficient matrix in the same matrix, append the constants, and then go to town with those. Okay? That was Gauss-Jordan elimination, or Gauss elimination and Gauss-Jordan elimination. Now we're not. We're going to separate this and have a coefficient matrix of 3 by 3, in this case, the unknown matrix, the variable matrix here, and then the constant matrix over there. They're actually vectors as well, and they bold them like they were naming vectors. Okay, so this next example is pretty much a piece of cake. And there's a reason we're doing this. It may not seem like we're doing much of anything. It says solve this matrix equation where, well, this isn't what I was thinking it was going to be. AX equals 0. That's a 0 vector, meaning all the elements are 0. Where A is, and it doesn't have to be square. This one is not 1, -2, 1, 2, 3, -2. And X is, the X vector is simply X1, X2. Okay? No, X3. Okay, I forgot X3. Okay? And that has to be 3 elements there. Let me clean that up just a little bit. Okay. I'm sorry. Okay. And your and the 0 vector here has to be, this is a 2 by 1, 2 by 3, I can't count. This is a 3 by 1, which it has to be for the 3's to wipe out. So this has to be a 2 by 1. That's what's left over. So this is just 0, 0, which, of course, well, okay. That's what you got. Okay. It says solve the matrix equation that. Okay. And then they proceed to do the same thing we used to do, Gauss-Jordan elimination, which we could have done that without writing this as a matrix equation. But let's do it because they said to. Okay, this would be a 1, -2, 1, 0, and a 2, 3, -2, 0. Okay? Now, what do you want to happen first? First entry to be a 1. It is! We don't have to do a thing. What do we want next?
You want to make that a 0.
0. How do you do that?
We want to subtract 2 times the top.
Okay, -2 row 1 plus row 2. I do it both ways sometime, but somebody, I think it was Muhammad, complained when I changed. So I'm going back to do the way I originally did it. So He won't be complaining. This is for you, Muhammad. Okay. So we leave the first row alone. 1, negative 2, 1, 0. And the new second row becomes 0. I believe it's 7, isn't it?
Oh, because, yeah, it's 7, yeah, because it's the wrong way.
Okay.
Maybe minus 4.
Negative 4. This doesn't look good, does it?
What's the top number in that line?
That's a 0.
Zero?
Yeah.
Still a 0 then.
Yeah. It stays a 0. All right. Yeah, I was going to say, this is not a pretty sight. What do we want to happen next? We've got a leading one here with zeros below it. What do we want next?
Well, we want to add 3 times the top row.
Okay.
To get that down to a leading 1.
If we did that, this now loses and doesn't become stay at 0.
Yeah.
So you can't do that.
Yeah.
I mean, you could do it. That make that a 1, but then it wouldn't have a 0 in front of it.
Right.
You lost the
point.
value. So how do we get a 7 to become a 1? Divide by 7.
Oh gosh.
Yeah. Okay.
This is again not resolved.
Okay. So row 2 divided by 7 is the new row 2. So this becomes, didn't mess with row 1 at all. That'd be 1, negative 2, 1, 0, and then a 0, a 0,
that'd be 1.
1,
And then a minus 4, 7.
negative 4 sevenths, I can't write, and then a stays a 0. That's the beauty of these homogeneous equations. That last column always stays a 0. Okay, now since they said we're doing Gauss-Jordan, we got to make the, sorry. Okay, you got a 1 here, 0 below, a 1 here. To do Gauss-Jordan, you got to get a 0 above. So this time we do what? You want this to become a 0. Using this.
Okay, so we can add 2 times.
2 times row 2 plus row 1. Okay? I'll go up here with this one. And we're changing the top row, so we'll leave the bottom row alone. 0, 1, negative 4 sevenths, 0. One of my favorite numbers of all time. And then the top row becomes 1, 0.
My fractional math.
Yes.
Oh gosh. It's 1 and 1 7, right?
That's correct. Only a negative.
Negative.
Right. I was trying to clean it up and I lost it all. Okay. So that becomes a negative 8 sevenths plus 7 sevenths is okay. And then the last one becomes a stays a 0. All right, we've done as much as we can. We've got our leading ones in each row, 0s above and below them. So basically we have a parametric equation here for that third variable, the x3. So we let that be, what's your favorite parametric letter?
Let's do C.
T, that's everybody's favorite, okay? So we'll let x sub 3 equal t, okay? The first equation then would read x sub 1 minus 1/7 t is equal to 0, right? T doesn't look much like a t. So that means x of 1 is equal to t over 7, right? Add 1/7 t to both sides. The second equation says that x2 minus 4/7 t is equal to 0. So that means, I said t but didn't write it in, 4/7 t is equal to 0. So that means x sub 2 is equal to 4/7 t. So here we have your generic ordered triplet that gives those three values, x1, x2, x3, is t over 7, 4t over 7, t. If you wanted to clean that up a little bit, multiply everything by 7, and you get t, 4t, 7t. That's a lot cleaner version of it. And pick a t, any t, that ordered pair, either one of those ordered pairs will give you a solution for that system of equations. Now, they went with my second choice here, t, 4t, and 7t, which, if you wrote it here, yuck, this would be t, 4t, 7t. That would be your x1, x2, x3 written as a column vector, which you could then write as a coefficient 1, 4, 7 times the scalar t. And they actually wrote it in front rather than behind. And any scalar multiple of that column matrix would be a solution, including 0, 0, 0, which you know has to be a solution, because I've already, I guess I never wrote it down per se, but for this plus this to be 0, and this plus this to be 0, obviously the trivial solution will work, and the trivial solution is part of that. Let's set t equals 0, and you have 0, 0, 0. But any other t you choose, plug them in, and you get solutions as well. And they list a couple of them there. 1, 4, 7, 2, 8, 14, 0, 0, 0, negative 1, negative 4, negative 7. Any t multiple of those will work. Now, that was all great, okay? And I guess they just had you do it to get you, because we'd been a few days without doing a Gaussian elimination, so let's do another one. Now they're going to go back to something they introduced a few pages earlier, a partition matrix, okay? And a little bit of review of what this is. That system of AX equal B that we had there. I'll straighten this up. I know it made that go out for a moment. It'll be back. Okay. AX equal B. Okay. That's a system of equations. Okay. They didn't specify how big A is, what dimensions A has, how big B, X or B are. Okay, but as long as they work, we're going to go back and do the same thing or close to the same thing we did before. This is A11, A12, A13, dot, 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 to A1N. A21, A22, A23, dot, 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 to A2N. A31, my A's get worse and worse. A32, A33, dot, 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 to A3N. And then dot, 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 this down to, you get a M1, a M2, with a dot, 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 and a dot, 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 a M3, and then a dot, 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 everywhere, dot, dot, even here, a M N. Okay, there's your A matrix, however big it happens to be. M rows, N column, that can be any that you choose. But once you've chosen that, then your X is somewhat fixed. It has to be a column, X of 1, X of 2, X of 3, dot, dot, dot. How far does it go? Again, go back and name the size here. This is an M by N. M rows, N columns. Okay? So this has to be an N by 1. It has to be. It's just one column, so this goes up to, yuck. So used to writing A's, I wrote an A. X sub N. Okay. All right. Where N may be different from M. Okay? Because these two sort of wipe out here. Okay, and what does that leave your B to be? B1, B2, B3, dot, dot, dot. Well, you have to have the same number of B's as you have equations, right? So that's B sub M. So that's why we saw in the last one, the X went up to 3's, but the B's only went to 2's. They don't have to be the same. X goes to N, B goes to M. Okay? All right. Now, and what they do is write this over and over again, and okay. And I know what they're doing. Let's do it. Seems like they could have saved some time and space here, but matrices, you don't save time and space. I mean, you take up a lot of space. Let's do this math here. Okay, the matrix multiplication. That would have been A11 X sub 1 plus A12 X sub 2 plus A13 X sub 3 plus dot, dot, dot plus A1N X sub N. Right? And that's the first row up, and this is equal to B1, by the way. Okay? Has to be. The next one says A21 X sub 1 plus A22 X sub 2 plus A23 X sub 3 plus dot, dot, dot plus A2N X sub N. Okay? Next one would be A31 X sub 1 plus A32 X sub 2 plus A33 X sub 3. I just love this stuff. Plus dot, dot, dot plus A sub 3 N X sub N. And then you dot, dot, dot down to the bottom until you get to, and I'm running out of room down here, A sub M1 X sub 1 plus A sub M2 X sub 2 plus A sub M3 X sub 3 plus dot, dot, dot plus A sub M N X sub N. Okay. And this is that B vector. I'm just not going to write it again. I'm just going to get lazy like they do and call it B. Okay, but we know it's those numbers. Okay. Now, if you'll notice, this first column here, now these are the things that add together to form that B, but this first column here has a common X1 everywhere, right? So you can take out this first column of your coefficient matrix, and do it times x1, plus your second column of your coefficient matrix, multiply that by x2, plus your third column times x3. And basically what they're doing is, and I don't have room to do it, they do, they got a whole page here. I'm just going to equal this on this side and see if I can get away with that. They put the x1 in front, I'd put it at the end, but it doesn't really matter. This will be a11, a21, a31, dot, 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 a m1 plus x sub 2, a12, a1 or 22, a32, dot, 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 down to a m2. Goodness, my stomach's growling. Plus, and they keep on going. I don't have room to write them all in, but you see what they do. In fact, they stop early and just do dot, dot, dots. Okay? Now, what this is saying is you have a linear combination of your columns here with the unknowns here. The first column, second column, third column. There's some things that give you this P. Okay? And these form column matrices here, which you could name A1, A2, A3, and so on, all up to A sub n. Okay? Now, A sub n because you have n of these. Okay? So, all right. I've run out of room, so I'm going to get to the summary at the bottom. And this is what we've got there. Exactly what we just did. The matrix product, A times X, where X is the unknown array, okay, column vector or column matrix. This thing is a linear combination, okay, of the column vectors A sub 1, A sub 2, A sub 3, dot, 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 up to A sub n. That form the coefficient matrix. Okay. A. These are the column vectors of that matrix A. Okay. Now, that's just given. A sub X, that matrix A times column vector X is a linear combination of the column vectors of A, A1, 2, 3, and so forth, that form the coefficient matrix of A. Okay? And they summarize it here. X1 times A11, A21, A31, dot, 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 down to A M1 plus X sub 2, column vector A21, A22, A23. Goodness gracious, I can't read my own writing here. I get sort of carried away, and it keeps getting smaller and smaller, and I can't read it. A sub 2, 3, dot, 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 down to A sub M. I blew this again. 2, 1, no. Sorry. Okay. This is driving me nuts. Okay. Okay. All right, let me try that one more time. A sub 1, 2, A sub 2, 2, A sub 3, 2, down to A sub n, 2. Okay? Plus x sub 3 times the column vector A sub 1, 3, A sub 2, 3, A sub 3, 3, dot, 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 down to A sub M3. For some reason I have M2, MN here. Ah, wrong one. That's a 2. I think it meant to be a 2, but it looked more like an N. Okay. Plus dot, 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 plus x sub n. I want to make sure I got my, and this will be A sub 1 n, A sub 2 n, A sub 3 n, dot, 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 down to A sub m n. Okay. That's your linear combination. Okay. Now, furthermore, that system, AX plus B, AX is equal to B, sorry, AX equal B is consistent. That means it has a solution. Okay, may have more than one, but it has at least one solution. If and only if, all right, here's Vince. All right, is consistent if and only if. Now that's one symbol for if and only if. Another one is IFF, or you can write it out, if and only if. B, this vector B, can be expressed as such a linear combination. Okay, now that sounds like it's double speak, you know. Can be expressed as such a linear combination where the coefficients of the linear combinations are a solution to the system. B, not P, are a solution of the system. Okay. Now, it sounds like or feels like you're going around in circles, okay? This is consistent if and only if B can be expressed as such a linear combination when the coefficients of the linear combinations are the solution to the system. What? Well, yeah. If this does equal your B's, then that equals to B. I mean, that's really what it sounds like it's saying, but it really is a lot better than that, I think. Okay. So let's go to, well, we keep coming, don't we? All right, Muhammad is here. All right. We've now got at least more than half the class here. All right. Now, let's do example 7 and see if some of this clears up a little bit. Okay. All right. Here's a linear system. X sub 1 plus 2x sub 2 plus 3x sub 3 is equal to 0. 4x sub 1, merely creative thing here, plus 5x sub 2 plus 6x sub 3 is equal to 3. 7x sub 1 plus 8x sub 2 plus 9x sub 3 is equal to 6. Okay. Now, doing what we did before, not like we've done before, but like we just did just now, we can write this as x sub 1 times this row vector here, 1, 4, 7, plus x sub 2 times, column vector, 2, 5, 8, plus x sub 3 times 3, 6, 9, and that's equal to 0, 3, 6. All right. Now, they set it up, act like they're going to do something with it, and go back and do Gaussian elimination again. Which, yeah, why? Okay. So let's do it. That would be 1, 2, 3, 0, 4, 5, 6, 3, 7, 8, 9, 4. Do Gauss elimination. We've got the one where we want it. So let's do our other. What would be the next step? Yeah, negative 4 times row 1 plus row 2. Okay, that should give it to us. So we're using row 1, 1, 2, 3, 0. And it becomes what? 0. Is it negative 3? Okay. Okay, wait just a second. My pen drug. I feel like I'm drugged. I can't breathe. And what was that, 3? Okay. All right. And then what do we do next? Negative 7, is that what you said? Oh, okay. Yeah, we'll do that. Okay. I was going to go and clear out the next one. What does it become? Negative 7, row 1 plus row 3, right? Okay, and what does that give us? 0. Minus 14 plus 8. Negative 6. Okay. Okay. That's a 9 here. Okay. Okay, and that would be a minus 12, right? Okay. And let me make sure that's right. That is a 6. It looks like a 4, but that's a 6. I don't know how I got to make it look like a 4, but okay, I don't think I had changed anything there. Huh? Ah, goodness gracious. I changed the 4 to a 6 and made it a 4 again. It's been that kind of day. Okay, 6. Okay. All right. Now what did that become? That stays a 6, right? Now, what do you notice here? Is what?
Divide the second row by negative 3.
Yeah.
The third row by negative 6.
Right. And what do they become then?
They give you 1, 1, 2, and -1.
Yes, both of them do, don't they? That gives you 1, 2, -1. This gives you 1, 2, -1, right? If you divide by -6. So those are identical rows, so you can subtract one from the other, or even right there, you could do 2 times, or -2 times row 2 plus row 3, you get all zeros, right? Okay. So you have an infinite number of solutions, okay? So let me write down what you just said. Now, did they say Gauss-Jordan? No, just Gauss elimination, okay? 1, 2, 3, 0, 0, 1, 2, -1. That's what you said, right? And this one would be 0, 0, 0, 0. Which at least, you know, there are an infinite number of solutions. If that had been 0, 0, 0, 17 or something like that, no solutions, okay? Because you have to have, same thing, the bottom row has to be all zeros. But that's what you would get, right?
I thought with the Gauss elimination we would want a 1 on the.
That's what you want to have, but it's not going to happen, right? Because if you were to do -2 times this row, add it to this row, that'd be a 0, 0, 0, 0. They all go to zeros. You can't stop it. They're all zeros. That means this is a dependent system, okay? And you could assign a parameter to that third variable, x of 3, or whatever they call it, yeah, x of 3, say t, that was been our favorite before. And this gives you x sub 2 plus 2t is equal to -1, so x sub 2 is equal to minus 2t minus 1. Then plug that in for up here, you get x sub 1 plus 2 times a negative 2t minus 1, that's x sub 2, plus 3t is equal to 0. So that says x sub 1 is equal to, that is a minus 4t plus 3t would be a minus t, so add it to the other side, you get that, and this would be a plus 2. Okay, so x sub 1 is t plus 2. So here's your ordered triplet then, t plus 2 minus 2t minus 1, t. Okay, let's see if that's what they got. I don't think they, oh, and then they just plug in a value and say one of these solutions is 1, 1, -1. Okay, let's put a -1 for t, then this would be a positive 2 plus 1 would be 1, and that would be a -1 plus 2, that would be 1. Sure enough, that would be one possible value. There's an infinite number of values, okay? Now, that is, B can be expressed as a linear combination of the columns of A. That representation of one column vector in terms of the others is a fundamental theme of algebra, okay? Linear algebra. Okay, they stop there. Sure, at some point they'll come back to it, but they're just going to leave it there. Now, here we go back to partitioning matrices, which is what this was called to begin with, but we've only done it in a very limited way. And it says, just as you partition A into columns and X into rows, it's often useful to consider an M by N matrix partitioned into smaller matrices, not just columns and rows. Excuse me. Here's one. And again, they just sort of throw this stuff out there and really don't do much with it. Okay? So I'm wondering, why throw it out there? Later they are going to recall it back, but why don't you just wait till you're going to need it and then do it? But this is just, again, it's rather large. 1, 2, 0, 0, 3, 4, 0, 0, negative 1, negative 2, 2, 1, okay? Now, that's just a matrix, a 3 by 4 matrix, just out there. They say, well, why don't you partition it this way? Okay, fine. And you could do that, okay? And then they say, well, why don't we partition it another way? And that's another fine. We'll do it. This time it was partitioning it this way, okay? And this you could name C1, C2, C3, and C4, because you have column 1, column 2, column 3, and column 4. Or you could partition it this way. I'm being really lazy here, so I don't have to rewrite them every time. And this would be by row partition, okay? And that would be R1, R2, and R3. Okay? Whatever that top one is, that would be a row, row, row. Okay? Your boat. Okay. And they just say you can do it. They just talked about partitioning, and they really don't do much more with it, except that one example 7, which they sort of just kind of left hanging there, but it was fine. Linear algebra applied. Now, I don't know if you're interested in this, but it is a pretty interesting phenomenon. I'll put it that way. Many real-life applications of linear equations involve enormous numbers of equations and variables. For example, a flight crew scheduling problem for American Airlines required the manipulation of matrices with 837 rows, more than 12,750,000 columns. I don't want to do that one, okay? This application of linear programming required that the problem be partitioned into smaller pieces, then solved on a Cray supercomputer, even after you got it down into smaller pieces. Yeah, yeah. So, and that finishes 2-1, by the way. Homework exercises here: do either 1 or 3 or both. Do any of the odds 5 through, 11. Then do either 13 or 15 or both. I guess they want you to do 13 and 15. Then do, wow, my throat's hurting. Any of the odds 17 through 29. Then do any of the odds 31 to 37, 39, any of the odds 41 to 47, either 49 or 51, 53, 55, 57. Now here again, they introduce a new concept here, not in the text, in the problems, in the exercises. They give you a definition of a diagonal matrix, okay? And in these two examples, 57, 58, we're only doing 57, they have you do something with it, okay? So there's a definition. Your diagonals are numbers, and your matrices, everything else in it is constant. Okay? Then 57 requires the use of diagonal matrix, and then 59 has a property of diagonal matrix. There's a guided proof at 61 if you're interested in proofs. There's a trace, okay, here's another definition. A trace of a matrix, okay? And that's number 63 and 65. There's another proof. All right. Seeing how many of these, there's just so many of them here. So the trace is defined in the dark type, and then you use it in 63 or 65, and it's proof in 67. Then do any of the odds 69, wow, to 73. There's a guided proof, there's proof of 75. You can do 77, and okay, 79 starts some practical applications. So do any of the odds 79, well, 79 or 81. Then they have what they call block multiplication, which goes back to the partitioning they introduced, but didn't tell you what to do with them. So now they show you what to do with them in 83. And then there's a true-false 85. And then there is a column matrix T. They don't define what that is. You can try 87 if you want to. Wow. Okay, that finishes 2-1. And we're out of time. So we're way out of time. So we'll begin next time with 2.2.
Oh, you did? No? I just thought you were waiting to finish what you were doing.
Well, I was trying to figure out how many of those to do, and